Welcome to the Introduction to Data Science series. How are you doing? It's been long since our last session and a lot has happened since then. I had my ISB graduation, I recently rejoined Nissan as a data science manager, and I also shifted to a new city. In the middle of all this, I did not forget where we left off and how I want to continue our data science sessions. So if you remember, we started the Introduction to Data Science series by walking through the end-to-end data science development process. Then we talked about the different kinds of data science problems that we encounter, namely regression, classification, time series forecasting, recommendation systems, A/B testing and optimization. After that, in the third and the fourth sessions, we talked about regression and classification and gave a quick overview of the end-to-end knowledge that is required for a beginner and also for an intermediate person looking to brush up his knowledge. Now, in this session, I would want to talk about time series forecasting, which is another essential area of machine learning. While regression and classification are more classically taught in machine learning, time series forecasting is generally thought of as a different subject, but it is nonetheless as important as regression and classification. So why is time series forecasting so important? Time series forecasting is very important because time series are used everywhere. For example, if you want to predict the sales or demand of your item for the next few months or the next few days, then you model the data as a time series and look to forecast it, and that has high value implications. There can be climate forecasting, and forecasting is used in many areas. Now let's dive into the technical aspects of time series forecasting. Alright, so as you can see, time series is basically nothing but a sequence of data observations at regular time intervals. The time intervals can be days, months, seconds, milliseconds, whatever it may be, but they need to be regular. That means if I am having a data point at 1 second, the next data point at 2 seconds, the third data point has to be at the third second, because the interval between the first two data points is that of 1 second. So the interval needs to remain the same. If it is irregular, then it is not a time series. Alright, now let's look at some of the components, some of the basic components that we need to keep in mind. There is the trend, which commonly, as you would think, is the time series increasing over time, is it decreasing over time, and so on. So in this particular example, you can see that the time series is increasing over time, so it's a positive trend. Another common component that comes very quickly to us is seasonality. Seasonality basically means, is the data having some kind of a pattern in it? Is it moving up and down at a fixed time interval, right? So behaving according to seasons. In this particular example, you can see that the time series is going up and down within one tick on the x-axis. So it's going up and down within one tick. The next tick again it is going up and down, and while the overall trend is increasing, there is a very clear seasonality in the data, right, which is happening within one tick or one time period. The next important component that we should keep in mind when we are thinking and looking at time series is cyclicity. Cyclicity is basically the movement of time series up and down over a large period of time or a large number of time intervals. It need not be regular, right? Unlike seasonality, cyclicity need not be at a regular time interval. For example, here you can see that across a number of ticks, the time series is moving up and it is moving down, right? Which is denoted by this larger tick, and then again it is moving up and moving down. And all the while, there is some seasonality present, which is at a tick level, which is at a time period level. It is going up and down, but the overall trend is going up and down as well. So the overall trend, as it goes up and down, that is called as cyclicity. And you can see that the length of the time period for one cycle is different from the second cycle, where the second cycle is smaller in this case. Another component, right, in any time series is the noise. What I mean by that is, this looks like a very simplistic time series. If you would have seen stock prices, you can see that the time series is very volatile, right? It doesn't follow a clear trend or has a very clear cyclicity or a seasonality to it. That's where the noise aspect comes out. When you remove the trend, seasonality and cyclicity, what you can see is the noise. The noise looks something like this, and it is stationary, right? Let me come to the stationary bit a little later, but all I wanted to look at here is if you see something like this, where the variance is not increasing, that means the spread of the time series is not increasing over time. It is lying between these two, imaginary lines, right? There is no clear pattern in the variance. It is of constant variance or near constant variance, and there is no trend, there is no seasonality in it, right? Because the trend is flat, the seasonality is also not there because there are sudden spikes and sudden dips, and there is no cyclicity as well. So this is noise, and this is stationary time series, which means exactly that there is no trend, there is no seasonality in it. If the seasonality didn't have a trend, didn't have a seasonality, but it still had a non-constant variance, which means the spread was, instead of between a certain limit, the spread was increasing over time or decreasing over time, right? If you look at something like this, if you look at this as a time series where the variance is increasing over time, then this is not a stationary time series. So we would apply certain kind of transformations to make the time series stationary before we can model it using ARIMA, which is a model which we will be talking about very soon, right? So stationary time series means it has to have a constant variance or a near constant variance, no trend, no seasonality, and that's it. Alright, now we have talked about time series and the basic components. Let's dive a bit more deeper into some of the metrics which characterize time series, and these are autocorrelation and partial autocorrelation. We are talking about these metrics specifically so that we can talk about how to model and forecast time series using ARIMA, which is one of the most used methods in time series forecasting, and it performs really well. What is autocorrelation? As the term suggests, autocorrelation means the correlation of a time series with itself at certain lags. That means if you have a time series and you want to see how the lag 1 of the time series, if you lag the time series by one time interval and correlate that with itself, what is the correlation of the time series with itself, right? That's why there is an autocorrelation. That's why there is auto in this particular metric's name. Let's assume in this example that the autocorrelation that we want to observe at is for lag 2, and this is the time series that we are observing for different years: year 1, year 2, year 3, year 4, year 5, year 6, and the data points are so on. Now to observe the autocorrelation at lag 2, what it is basically doing is it is lagging the data point 2 time intervals back. So the year 6th data point comes to year 4th data point, the year 5th data point comes to year 3rd, and so on. And now with this newly created time series, which is at the bottom 30, 40, 45, 54, we want to observe the correlation with the original time series, which is non-lagged, right? And the correlation which we obtain, we call it the autocorrelation at lag 2. We can do it for lag 3, lag 4, and so on. Alright, now let's talk about partial autocorrelation. As the name partial autocorrelation suggests, there's something about it where we are talking exclusively what is the relationship between that lag and the time series itself. In a way, think of a partial derivative. The change of a variable with respect to another variable, keeping all the other variables constant, right? In this case, we want to remove the effects of the intermediate lags when we are obtaining the correlation between a time series and a lagged version of that same time series. So in this example, lag 2 of autocorrelation, what we basically want to remove is the effect of the lag 1 time series, right? We want to remove the effect of the lag 1 on the lag 0, which is the standard time series, the normal time series. Why? Because lag 2 will affect lag 1 because the time series is flowing through time. So what happens before, say in the month of March, will affect what happens in the month of April. What happens in the month of April will affect what happens in the month of May, right? We only want to see what happened in March, how did it affect what happened in May, keeping the effect of April constant. We want to remove that effect somehow. We want to partial it out. That's where partial autocorrelation comes into the picture. Alright, so here what you can see is the autocorrelation function plot, and here you can see the partial autocorrelation function plot. One thing that would strike you very quickly is that the autocorrelations are decreasing when we look at larger lags, which makes sense, right? The observations which are the nearest in time would be most correlated than the observations which are far apart in time, which is basically at larger lags. That is why overall you would see a decreasing autocorrelation. Similarly in partial autocorrelation as well. But interestingly, at the autocorrelation function, what you also see is that there is a kind of a cycle which is going on. The autocorrelations are decreasing, then they are increasing, then they are decreasing, and so on. So if you look at this particular point, like these are two peaks, and this is the third peak. Why are we observing this peak suddenly, right? If you think about it, this is an indicator of seasonality. What that means is at a particular lag, let's take it to be, so let's suppose this is at the 12-month lag and this is at the 24-month lag. What it is saying is how the time series is correlated with itself when we lag it by 12 months, right? If you're looking at January to December of 2021, right? When we lag it by 12 months, we are comparing January to December 21 data against January to December 20 data, right? Those two series we are comparing, and they are bound to be correlated, right? Because both of them would likely have a common seasonality if what we are looking at has a yearly seasonality, right? So they would be correlated if we just plot them together, right? That's why the autocorrelation function spikes up wherever the seasonality is present, and from this we can infer what is the seasonality that is present. At what time interval is the seasonality observed? Is it quarterly? Is it monthly? It can be anything. Alright, and what are these lines that we are talking about? These lines are the significance levels. So the significant level comes into the picture when we basically want to use this autocorrelation function plot to find out what is the order of the moving average model that we are using in the ARIMA model. So don't worry about it, I'll just go over it shortly. But just to give you a sense, here there are 3 lags, right, which are crossing the significance level threshold, and here we would say that the order of the moving average model that we would want to consider would be 3. So the moving average model gets its order from the autocorrelation function, and similarly the autoregressive model gets its order from the partial autocorrelation function. Here you can see in the partial autocorrelation function there are 3 lags which are continuously crossing the threshold, whereas the 4th one is not, the 5th one is. But since the 4th one is not crossing it, we would consider the order to be 3 for the autoregressive model. Alright, now let's move on to the ARIMA model, which has 3 parameters P, D and Q. So what does ARIMA stand for? ARIMA stands for Autoregressive Integrated Moving Average. The autoregressive model has an order of P, which is determined by the partial autocorrelation function plot. And what autoregression means, as the term suggests, is that a time series, let's say we want to predict what happens next month, that is dependent on what happened this month, the month before that, the month before that, and so on, till a period of P months back into time. And we are basically creating a regression equation where we are taking lag 1, lag 2, lag 3 and so on till lag P. We are getting those variables, and we are creating a regression model using those X variables to predict the Y variable, which is our forecast, right? So that's what this equation shows. Yt hat is beta naught, which is the constant, plus beta 1 parameter into yt minus 1, the lag 1, plus beta 2 parameter into y2 minus 2, which is the lag 2, and so on till lag P, right? Because you can see t minus P here, right? So this is starting from t minus 1 till t minus P. So there are P lags that we are looking at, which is the order of the autoregressive model. What does integrated mean? Alright, So this is the more important part of what an ARIMA model can do and where it can perform well. So an ARIMA model has the assumption that the time series is stationary, which means that it has a near constant variance, no trend and no seasonality. If the time series has trend or seasonality, we need to remove the trend and the seasonality in order to make it stationary. And if it has non-constant variance, we also need to do a Box-Cox transform, which is a power transformation, to make the time series have a constant variance, right? So here we are talking about the differencing aspect, where if you have a trend, you would then difference the time series and you would keep on differencing it, say 1 time, 2 times, 3 times, until the time series looks stationary, right? And there are certain tests to find out whether the time series that has been differenced is stationary or not. Here what this equation is showing is basically if difference is equal to 2, then this is what the new time series would look like. In the bracket you can see that this is when the time series is differenced 1 time, right? These two brackets show that yt hat minus yt hat minus 1. So the time series is getting differenced 1 time, yt hat minus 1 minus yt hat minus 2. This is also basically showing that the time series has been differenced 1 time, right? If you think about it, yt minus 1, yt minus 2. Okay, you difference the time series 1 time, so you get data points of yt minus 1, you get a new data point, then you get another data point as yt minus 1 minus yt minus 2. This is your second data point in the differenced time series, which has been differenced 1 time. Now if you want to difference it the second time, from the new time series you would again difference the 2 data points, which is basically yt hat minus yt hat minus 1 minus yt hat minus 1 minus yt hat minus 2, right? So this is what a second order differencing looks like. Now let's talk about the moving average model, which has an order of q. And if you recall, the order q is determined from the autocorrelation function plot. Basically, a moving average model is built with x variables as the lagged forecast errors, right? And I will not go into how the lagged forecast errors are calculated and how they are obtained, but all you need to know is a moving average model can be shown as yt hat, which is the forecast, is equal to the mean mu plus the error term, right, at time t, plus beta 1 parameter into error term of lag 1 and so on till lag q, right? This means if we want to look at an order 0 moving average model, it is simply mu plus epsilon of t, which is the error in the t time period. In ARIMA, there are basically a lot of variations, so you can have different combinations of PD and Q, and certain combinations correspond to certain models like exponential smoothing, simple exponential smoothing for example. So you can derive simple exponential smoothing from an ARIMA model with a certain combination of PD and Q and so on. And there's a very useful function which is known as auto ARIMA, which automatically looks at your time series, right, and finds these parameters for you depending on how much is the information criteria, right, the AIC and the BIC criteria, right. So you can simply use auto ARIMA in Python or R to get these parameters and to model your time series and then eventually use it to forecast into the future. Now we know that a lot of data is very seasonal in nature, and what if you also want to model the seasonality aspect of it, right? That's where you would also want to use a seasonal ARIMA instead of a vanilla ARIMA model. A seasonal ARIMA model has additional parameters capital P, capital D and capital Q for the seasonal part of the model, right, where M is the number of observations. Alright. We can also do multivariate time series forecasting. So for example, we are forecasting sales into the future, but we know that advertising spend also affects sales, and say suddenly we are doubling our advertising spend in the next month, right? So without accounting for the advertising spend, if our sales forecast would have been 1000 units, and we know this additional information that so far whatever the advertising spend has been, it's suddenly getting doubled, seeing a spike, we would also want the forecast to use this information and basically forecast the sales to be something more than 1000, because advertising directly affects sales, right? So in order to incorporate this new information which is given by advertising, which is a new variable other than the time series variable of sales, what we need to do is add this exogenous variable, right? It is an external variable which we want to add to the time series forecasting model, right? That's known as multivariate time series forecasting because there are more than one variable involved, multivariate, right? Here we can use Arimax and Sarimax models. The only consideration when you are looking to forecast using these models is that you also need to have a forecast of the X variables, the exogenous variables that you are planning to use. The historical data will be used to basically build a model, but in order to forecast your Y variable into the future, you also need a forecasted value of the X variable, what it is going to be. And with all this information, you can then go ahead and forecast the Y variable, in this case sales. Now this is all good and well, and you have built a model, you have understood how an ARIMA model works, you have understood about autocorrelation, partial autocorrelation, and then we come to the final step. How do you validate your model, right? Before using it to forecast something and to use that forecasted value, you will need to be confident about how strong and how good your model is. So that's a validation approach that we need to do. And that's where backtesting comes into the picture. This is a term specifically used for time series. There are two approaches to backtesting, sliding and expanding, and I will come to it shortly what these mean, right? But basically what backtesting means, as the term suggests, you're going back in time and testing your model, right? So basically, let's look at this first row here where there are 3 data points which are encircled and 1 data point which is encircled with a cross inside it, right? What it means is that year 1, year 2, year 3, these are the data that we have, and we are building a model predicting for year 4 and then judging what our error is for year 4. Then we are going to the next iteration. We are looking at year 1, year 2, year 3, year 4. We are basically adding this additional data point of year 4. We are building a model. We are predicting on year 5, checking what the actual for year 5 is, getting the error. Then in the next iteration, we are taking year 1, year 2, year 3, year 4 and year 5. Basically adding another extra point of year 5, building a model, then seeing how it is performing for year 6, right? And then we are averaging out the errors that we obtain for year 4, year 5 and year 6 using this modeling approach. So this is basically showing us how our model would perform if we go back in time, how it has actually performed. And then when we have a reasonable amount of error, right, when the accuracy is good enough, what we do is we train the model on the entire data till year 6, because all of this is the actual data, and then use the model that we have trained and fine-tuned to predict for year 7, which is the forecast that we will be using, right? This is the validation accuracy that we will be quoting, and that is the forecast that we will be providing for year 7. So both of these are very important metrics to keep track of. Actually, the first one is a metric, the second one is a forecast, but that again will become a metric when the actual data for year 7 is obtained and we see what our test accuracy was for year 7. One technical detail here is that if you see, we always included year 1 and then we kept expanding the data that we needed to input into our machine learning model or time series model to forecast. So the window, if you look at, the first one was 3 years, the second one was 4 years, the third one was 5 years. This keeps on expanding. So this is an expanding window approach. Some people might argue, or in some use cases, we should argue that the oldest data points are not as useful for modeling. So in that case, we might want to keep the window fixed. Say, let's keep it to be 3. So in this case, if we are keeping a sliding window approach, the first iteration would be year 1, year 2, year 3. The second one would be year 2, year 3, year 4 instead of also having year 1, right? Because the window size is fixed, we will only have year 2, year 3 and year 4, the most recent 3 years, and then predict for year 5. Similarly, in the third iteration, we would only keep year 3, year 4 and year 5, which is the recent 3 years, and predict for year 6. So this is how we would do the sliding backtesting. Time series forecasting and building models which can forecast and model time series is a very vast topic, and it is very important for a data science and machine learning practitioner to understand the basics of time series, because there is a very big chance that you would be required to build a machine learning model for time series and use it to provide high value to your business. Alright, so that was all for today's session. Let me know in the comments if you liked it and any questions that you have. Make sure to like, subscribe and share the content on our channel, and follow me on LinkedIn and Instagram, the links of which are given in the description below.